Hello, class. So what we have going on today is we're going to look at a reaction where we're going to take a ester and use acidic conditions to convert it to a carboxylic acid. So that's a reaction that you need to know. We can also take an ester and use basic conditions to make a carboxylic acid. So the purpose here is to go through the mechanism and get you guys more comfortable being able to look at a reaction condition and predict what mechanism that you're going to use. So let's take a look at a generic ester. It looks like this. And let's treat it with some water, and we are going to have a small catalytic amount of acid. What is the mechanism to take this guy and convert it into a carboxylic acid? Now let's take a look at this mechanism here and go through it, and you tell me what you think. Go like that. So that will give us this. And then we have OH positive, just like that. Okay. And then we can do a proton transfer. We have a lot of water around. Do a proton transfer to get rid of that positive charge like that. And then we could bring this lone pair down and kick off the OR to give us our product. Now I'm going to shrink this down to keep it all on the same page here. And then we would have the OR minus, because there would be 3 lone pairs. Okay, so that's a proposed mechanism. And on the exam, if you did this mechanism, you would feel pretty good about yourself because you showed that you started with an ester and you got to the carboxylic acid. However, this mechanism that I just drawn is 100% wrong. Let me show you the correct way, and then we can compare and contrast why it's wrong. So what we have here is water in acidic conditions. So what that's actually going to do for us is it's going to create the hydronium ion. Whenever you are under acidic conditions, it is highly, highly unlikely for you to create something that's basic. And when you have a negative charge, that's a basic piece of the molecule. So this piece right here cannot form because it's acidic conditions. And then look, right here, I formed another base right here. That can't happen. We're under acidic conditions. So the mechanism in green is incorrect because we didn't factor in what conditions we were in, acidic or basic. We're under acidic. So the first thing that has to happen is going to be a proton transfer step. So if I redraw the hydronium to look like this, just rewriting it to make it look a little different, we're going to have a proton transfer step. And the first step is going to be that guy coming and grabbing that. We have a proton transfer step. So that's going to give us plus some water. Okay. Now, do you see how I don't have any negative charges here? So what is that going to now do? Okay. Well, when we protonate it, that's going to make this carbonyl carbon more electrophilic. So then the next step is we can have a nucleophilic attack. So we are going to have a nucleophilic attack from the water, like this. And so we'll have an OH. OH, and I'm going to draw the other OH like that, just to help me with the mechanism. So here's our water. The water right here comes in and attacks. There it is. Now, what we're going to have to do is, because what's our ultimate goal? We want to make a carboxylic acid. So we need to get this guy right here, the OR, to leave. But we can't just make it leave like this. Okay, we can't just say, hey, leave. Because if it just left like that, what would we generate? We generate a basic species. And we're under acidic conditions, so that can't form. So we got to do a couple proton transfer steps to do that. So we're going to have a lot of water around. A lot of water. So we're going to take a water molecule and just do a proton transfer. So we're going to get this species now. OR, but what did we generate when the water attacked? We generated the hydronium. Now that hydronium, or the acid now, we're going to take the OR and convert that into a good leaving group. Now, so that's going to protonate it. So now it's positively charged. And we regenerated some water from that proton transfer step. Now, what do we have going for us? That is positively charged. So now it's a good leaving group. So we can take one of these lone pairs here, bring it down. Now that's going to leave. So that's positively charged. We have an OH. What left are HOR. So it's left as an alcohol. And then we just have one more proton transfer step. So we can take this water that was right here to give us our carboxylic acid compound. So there's more steps in this blue mechanism, but they're all just basic proton transfer steps. This is a nucleophilic attack, but everything else is like a proton transfer step. This one right here is we eliminate off the OR, but that is the correct mechanism because it doesn't break that rule of when you're under acidic conditions, you're not forming any negatively charged species or basic species. Let's see, what else is there to say about this? Oh, yes. I need to correct this in the fact that all these reactions right here are reversible. Okay, so let's just make sure we understand that. These are reversible steps. All right, so next we're going to take a look at what happens when we are under basic conditions. How does this mechanism change even though we get the same product? Now let's take a look at this reaction under basic conditions. So with hydroxide. Now that hydroxide is going to be dissolved in water. So we're under basic conditions. So what's the first step here? When we have hydroxide present or basic water, what's going to happen? We can have it directly attack the carbonyl carbon. Now, let's remember that these processes are all reversible. So what would we get? We would get this species. Now, is it okay that we generate a negative species or basic species? In this mechanism, yes, because we are under basic conditions. Okay. So what would be the next step here? Let's see here. What did we get? So the base came in. We could collapse that down. So let's see here. Here we have our tetrahedral intermediate. We can take that and collapse it back down, and then this can leave. Why is that okay? Is that okay? Look, a negatively charged species, a basic species under basic conditions. So that is okay. And that would be a legitimate mechanism for converting an ester into a carboxylic acid under basic conditions. So we can now also look at amines as well when they attack. So let's take a look at amines. So we could take a ester and treat it with a amine. And amines are really nucleophilic. And what are we going to get when we use that combination? When you have amines, they're basic and very nucleophilic. So it is okay to take an amine and attack the carbonyl directly without having to protonate the carbonyl oxygen. So you would get an intermediate that looks like this. Negatively charged, a nitrogen with 3 hydrogens. If it has 3 hydrogens and a bond to carbon, what do we have? A positive charge. It is okay to have a positive charge and a negative charge right next to each other. It's not the most stable thing, but it's okay. What you want to avoid when you're doing mechanisms is having 2 charges that are the same, a negative charge next to a negative charge, or 2 positive charges right next to each other. That's when you see something like these 2 things in your mechanism, then there's a high probability that you've done something wrong. But when the charges are opposite like this, that is okay. So next, what we're going to discuss let's take a look at something that's not acidic or basic. It's just kind of like neutral conditions. Like, what do you do there? So what if we take a acid chloride and treat it with water? Okay, what are we going to get? Well, if we do this reaction, we are going to get a carboxylic acid. So put that in your toolbox. Acid chlorides with water gives us carboxylic acids. So there's another way to make that. So, but what is the mechanism here? Well, when we look at it, now I'm going to go this way here, okay? Water is going to be able to attack the carbonyl directly. And that's going to give us O minus. And there's going to be a plus charge there. And our chloride. Okay? So what is our next step going to be? Is the chloride a good leaving group? Of course it is. So we can take this tetrahedral intermediate, collapse it down, and then kick off the chlorine atom. Now we have a double bond there, an OH, and that's our water. So this piece right here is that piece right there. And then we have the chloride that just left. It's a good leaving group. It's negatively charged, and that is fine. And the next step is just another proton transfer step. And we have a lot of water. Yes, we generated a chloride here, but there's by far way more water than this chloride. And that is why we're going to use water right here to do the proton transfer step. And then that's going to give us our carboxylic acid. And then we would have our hydronium right there. Now, go back to the taking ester to the carboxylic acid under acidic conditions. So, what I want to say is sometimes this leaving group can just leave. The chloride could just leave like that. In the basic conditions, the OR could just leave because we're under basic conditions. But remember when we were under acidic conditions, the OR could not just leave. It had to be protonated first. So when you're looking at your leaving group, can it leave under the conditions that you are in? And if it needs to be protonated in order to leave, then protonate it. All right, so we've gone through a lot of mechanisms here, and each one had a little different variation. But it's by looking at the conditions that you can be able to figure it out. So now what we want to do is how do we make acid chlorides. That's the next reaction that we want to look at and understand. So how do you make acid chlorides? One way to do it is to take carboxylic acids and treat it with thionyl chloride, and then you get yourself a acid chloride. Now, mechanistically, how does that work? Because look at what's happened. We've simply replaced a OH with a chlorine atom. And from our Orgo 1 knowledge, we know that a OH is not a good leaving group. So we got to figure out a way to convert that into a good leaving group. How do we get rid of it in order to have that chlorine replace it? So the mechanism is very telling and it helps us out. So if we draw out our thionyl chloride, it looks like this. Okay? And what we're going to do is I'm going to take this lone pair here, bring it in, and then these electrons are going to come and attack that sulfur and bring those electrons up like that. So we are going to come down this way to see what that looks like. So we have our R group, double bonded OH. So that's going to be positive. We're going to have our oxygen right there. And that's going to form a bond with the sulfur. And that sulfur has an O minus right here, a chlorine, and a chlorine, just like that. So the next step is going to take this guy and collapse it down, and then that's going to kick off a chlorine atom. So like that, plus our chloride, like so. And then the next step, we're going to do a proton transfer. We're going to take our chloride and do that proton transfer step. Let's see, plus HCl. Now what has happened? Let's do it in green. That right there is a great leaving group. Okay, so now that we have that great leaving group, we can use that let's see here. So the next part here is that we understand we have hydrochloric acid, right? And hydrochloric acid is an acid, so it separates out, kind of looks like this, all right? So what we're going to now do is use that chloride that was generated to act as a nucleophile and attack our carbonyl carbon right here. So that's going to come in and attack that carbonyl carbon. We formed a Texas carbon, so we've got to bring those electrons over like that. Okay? Just what marker? I have 4 markers in my hand here. Then we go up here. What's that intermediate going to look like now? It's going to be R O minus. I just attacked with a chloride. Still have the oxygen, sulfur there. We have a tetrahedral intermediate. Look what happens. We collapse it back down. Which is the better leaving group between these chloride and this guy? Well, this guy is the better leaving group. And look at that. That gives us our product. Isn't that pretty clever? Now, what's cool and interesting to me is at the beginning I said we had to get this guy to leave and replace it with the chloride, right? That's what I said. But mechanistically, that's not what's going on here, right? Because look at this oxygen right here. That oxygen, it's this oxygen right here. Look at the mechanism. It's that oxygen there. So this guy and that guy are the same oxygen atom. Just follow the mechanism. That oxygen, there it is, there it is, there it is, there it is, boom. It stays throughout the whole thing. What actually left was this one. That oxygen atom's the guy that left. Let's track it. So there it is, there, 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 and there, and then we see that it leaves. So pay very close attention to that. You will find on standardized tests, they will ask you which oxygen atom is that one. They'll be like, did this oxygen come from that one or that one? Okay. So it's really testing your understanding of the mechanism. So I already showed you this reaction in a little bit before all of this. Remember what happens when you take an acid chloride and you treat it with water? What do you get? Think about that for a second. You take a acid chloride, treat it with water. What do we get? We get a carboxylic acid, right? That reaction is simply called a hydrolysis. Hydrolysis of acid chlorides. And I already showed you the mechanism of how to do that. So make sure you know the name. Hydrolysis of acid chlorides goes into a carboxylic acid, and make sure you know the mechanism. And I showed you the mechanism previously. In the mechanism, remember that when you do this reaction, you generate acid. Go back to the mechanism. Make sure you remember that. You generate acid. So typically when you do this reaction, you do another step where you neutralize the acid. You just want to eat up all this acid, and you just treat it with the base. And typically you treat it with some pyridine to neutralize the reaction. Okay, the next reaction that we want to talk about is, let's see here. How do we make esters? What's a way to make esters? And what we're going to look at is how we can take an alcohol and the acid chloride to make an ester. So that's what our next reaction is. So the next reaction that we're going to look at is taking an acid chloride, treating it with an alcohol with a little bit of pyridine to generate our ester. And this reaction is called an alcoholysis of acid chlorides. So what do we notice here? Basic stuff. We have a chlorine. It has been replaced with an OR. So this OR right here is coming from that guy right there. Now, mechanistically, how is this working out? What are we doing? Well, we know that there's some lone pairs on that alcohol. Okay. Well, I could see a couple ways to actually do this reaction. Let me pause the video for a moment to double check, because there's multiple ways to do this. So we have our alcohol. Takes the lone pairs and attacks the carbonyl in this manner here. And then we're going to get a tetrahedral intermediate. Like so. And that guy has to be positively charged because there's 3 bonds on that oxygen. The tetrahedral intermediate is going to collapse, kicking off the chloride. Like that. And then we have a proton transfer step to give us our product. Now this is where there's a confusion, controversy, I don't know how to really say it, but it's a proton transfer step. So proton transfer steps aren't that critical. And what I mean by that is I'm going to show you all the possibilities here for this proton transfer step. We could have a proton transfer step where I take the alcohol, because we're going to have excess of that alcohol around, and that alcohol could come in and do the proton transfer step, which would give us an acidic molecule. We could also have, hey, we just kicked off the chloride, so there's chloride hanging around. So that chloride could have come and abstracted that proton to give us hydrochloric acid, right? And then we also technically we have the pyridine. That could have come and taken that proton. To get us to our product. So depending on what textbook or what source you're looking at, you might see all of these. But for our class, the textbook does talk about the reason why you add pyridine to this reaction is to neutralize the acid. And our textbook says, hey, we have to add pyridine to neutralize that species. So you can use when you do the mechanism, you can choose whatever base that you want here to do this proton transfer step. Do note that our textbook suggests that this is what's formed after that proton transfer step, and that's why you need to add the pyridine, is to neutralize this. Okay? But that is the mechanism of alcoholysis of acid chlorides. Now let's do an example or look at some of the issues with that. What if we did, let's say, a very simple primary alcohol treated with an acid chloride with some pyridine? What would our product be? Well, we're forming a ester, right? So you could look at it like this. You could look at it like this. We're going to replace that chlorine with that. That's one way to look at it. Or you could say, hey, we're going to replace this hydrogen with that. Doesn't matter how you look at it, as long as you can see that we have 1, 2, 3 carbons there. 1, 2, 3 attached to an oxygen, and then that oxygen is going to form a bond with that carbonyl, and then the R. So that is the alcoholysis of a primary alcohol. And that process goes very, very well. Okay? But then when you start introducing sterically hindered alcohols, so let's say we have a primary alcohol there, but a secondary alcohol there, and we treat it with a acid chloride molecule with some pyridine, we can selectively only react it with the primary and not the secondary due to sterics. So if you do this reaction with tenderness and care, you can, and I ran out of space. Let's just write it below. Okay, I'm going to write it down here. 1, 2, 3, 4, 5. 2, 3, 4, 5. You could selectively only convert this alcohol into an ester. And that's just based off of a steric argument. Now, I said with tenderness and care. What do I mean by that? You just have to watch the reaction very, very carefully, because it's going to selectively go for this one. But then once all of this has been reacted, if you keep forcing the reaction, like crank up the heat and keep going and going, yeah, I could envision us getting some of that to react. But if you monitor it very carefully, you can selectively only make the transformation with the primary alcohol due to a steric argument. Okay. Now what we can do is treat acid chlorides with amines. And that's called aminolysis. So we're going to look at that reaction next. So we have aminolysis of acid chlorides. That is in which you take your acid chloride, treat it with an amine, and you generate a amide. So put that in your toolbox. How to make amides. Here's one way. One thing to note, that you need 2 equivalents of this. And the reason why you need 2 equivalents is because the amine can act as the base and the nucleophile. So do you recall when we were treating acid chlorides with an alcohol? What did we have to do? We had to add the pyridine to mop up the hydrochloric acid that's formed. Well, when we have amines, we just do 2 equivalents of the amine to mop. One equivalent will mop up the hydrochloric acid that's formed, and the other amine will act as the nucleophile. So your amines, we could have, whoa, what am I doing here? We could have 2 equivalents of this amine, and that would give us this product. No, not that product. What are we doing here? RH. There, that looks better. We could also have 2 equivalents of this guy and get this product. So class, what do you think? Do you think that would work? Would we get a compound when we have a tertiary amine? Here we have a secondary and a primary. Do tertiary amines work? Now, I would suggest that you pause the video and do the mechanism and see if you can answer your own question. So let's take a look at a mechanism. Let's do it. Let's see if you can see if it will work or not. So let's do it with R2NH. Okay, let's do that. So what would the first step be? Going to attack like that. Negatively charged. We have our chlorine still there. Nitrogen H. R and R. So that nitrogen has 4 bonds, so that's going to be positively charged. So what's going to be our next step? Well, we have a tetrahedral intermediate that's going to collapse down to kick off the chloride. That will give us this species. Plus our chloride. Now we could take our chloride and treat that as the base to do the proton transfer step if we would like. That's kind of what's suggested. But if you would have used some of the excess of this amine right here, remember there's 2 equivalents of it. That could be the base that deprotonates this. So what we could say, we could just generalize it. Hey, there's a base here that's going to come and do the proton transfer step. And that's going to give us our amide. Now, going through this mechanism, what do you think? Do tertiary amines work? Will it form the product. Think about that. And we'll most likely talk about it in class. But it would be a good idea for you to already have your answer. Okay? Okay. Next, we can take acid chlorides and we can reduce them into primary alcohols. And we can do that transformation using lithium aluminum hydride. So we can look at the reduction of acid chlorides. And simply put, if we take ourselves a generic acid chloride and treat it with lithium aluminum hydride, and we're going to use that in excess. And then in step 2, you're going to have a aqueous workup. And when you do that, you are going to generate yourself a alcohol. So let's take a look into some of the details with this reaction. And why do we need excess and what's happening here? Let's kind of look at it mechanistically, figure out this reaction. As I go through the mechanism, try to answer the question, why do we need excess lithium aluminum hydride? So let's look at the hydride here. You know, that's negatively charged. And these hydrogens are very nucleophilic, like so. So then that's going to give us what? A tetrahedral intermediate. We added that hydrogen from the lithium aluminum hydride. We formed a tetrahedral intermediate and we collapse it down. Well, what's that going to give us? That's going to put the hydrogen there, double bond O there, and it has kicked off the chloride. So we've just generated an aldehyde, but I just said it goes to the alcohol. So what happens is we have an additional aluminum hydride. Where we do the reaction again. Now we have our alkoxide. So all of this right here, this is all step 1. Now we have to do step 2, which is simply adding water. And what's water doing here? If I redraw it like this, it's a proton source. We are doing a proton transfer mechanism, in which now we're going to then protonate the alkoxide to give us the alcohol. So that's the basic mechanism between the reduction of acid chlorides. Now there's some practical issues with this. We use excess, okay? And hopefully you can see why, because there's one equivalent to do the first, add the first hydrogen, and then you need a second equivalent to add another one. If you try to just use one equivalent of lithium aluminum hydride, you just get a mixture and a mess of products. It's just not going to be what we want. This transformation also of taking an acid chloride to an alcohol isn't very, it's not very practical. It can clearly be done, but we typically don't do it that way because of the fact that acid chlorides are generated from carboxylic acids. So if we have a carboxylic acid right here, we have to do a reaction to convert it to the acid chloride, and then you would do the reduction to get it to the alcohol, right? Like that. Why would you do that? Why would you go through this path to get an alcohol when you could have just taken the carboxylic acid, reduced it with lithium aluminum hydride directly, and get your alcohol in one step? So that is why we typically don't use acid chlorides to make alcohols, because it's just easier to start with the carboxylic acid and do it that way. So that's just a practical thing to be aware of. That's why we typically do this, because it just makes logistic sense, right? One reaction instead of a couple. Okay, so in the next video, what if you were doing this reaction here, okay, with the acid chloride, but you wanted to stop at the aldehyde? Remember in the mechanism how when you add the first hydride to the acid chloride, you form a tetrahedral intermediate that collapses, kicks off the chlorine, and gives us an aldehyde. And then the mechanism proceeds with a second addition of the hydride to convert it into an alcohol. But what if you wanted to stop at the aldehyde? How can you do it? And there is a way, and that is what we're going to talk about next time.